In RF engineering, signal levels can vary from extremely weak noise to very strong transmission power. If we use linear units, these differences become difficult to compare and manage in system design. In this lesson, we will learn decibels dB and dBm and how they simplify RF measurement, gain, and signal analysis. RF systems deal with signals that span an extremely wide range of power levels. A transmitter may output watts of power, while a receiver may detect signals in the range of nanowatts or even femtowatts. When expressed in linear units, these values become difficult to compare and intuitively understand. For example, comparing 1 milliwatt to 1 watt requires dealing with a factor of 1,000. When multiple stages of amplification and attenuation are involved, these multiplicative relationships quickly become complex and difficult to track. This is where linear representation becomes inefficient for engineering analysis. Decibels solve this problem by compressing large dynamic ranges into a logarithmic scale, allowing engineers to work with manageable numbers while preserving meaningful relative differences between signal levels. A decibel is not an absolute unit, but a relative logarithmic measure of ratio between two values. It is defined using a logarithmic function applied to power or amplitude ratios, which converts multiplication into addition. In RF engineering, this property is extremely useful because it allows gains and losses in a system to be expressed in a consistent and additive form. Instead of multiplying many gain factors together, engineers can simply add their decibel equivalents. This transformation makes system-level analysis much more intuitive, especially when dealing with cascaded components such as amplifiers, filters, and transmission lines. There are two important forms of decibel representation in RF engineering: dB and dBm. dB is used to describe relative gain or loss between two signal levels, while dBm is used to express absolute power relative to a fixed reference of 1 milliwatt. Using dBm, engineers can directly express signal power levels in a standardized logarithmic format. For example, 0 dBm corresponds to 1 milliwatt of power, while positive and negative values represent higher or lower power levels relative to this reference. This dual representation allows engineers to switch between relative system analysis dBe and absolute signal measurement dBm depending on the design requirement. One of the most powerful features of decibels is that they convert multiplication into addition. In a real RF system, signals pass through multiple components such as amplifiers, cables, filters, and antennas, each contributing gain or loss. In linear form, these effects must be multiplied together, which becomes complex as the system grows. In logarithmic form, each stage is represented in decibels and simply added or subtracted along the signal chain. This makes it much easier to calculate total system gain, link budgets, and signal strength at different points in a communication system. It also reduces computational errors and improves conceptual understanding of system behavior. In RF engineering, decibels are used everywhere because they provide a standardized way to measure and compare signals across extremely large dynamic ranges. Whether analyzing antennas, amplifiers, filters, or communication links, dB and dBm are the default language of RF system design. Engineers use dB to describe gain, attenuation, noise figure, and signal-to-noise ratio, while dBm is used to represent actual signal power levels in transmitters and receivers. This consistency makes it possible to design complex systems using simple additive calculations. Without decibels, RF system design would require constant handling of extremely large and small numbers, making analysis slower, more error-prone, and far less intuitive. In this lesson, we learned that decibels provide a logarithmic way to represent signal gain, loss, and power levels in RF systems. They simplify complex multiplicative relationships into simple addition and make it possible to analyze entire signal chains efficiently. In the next lesson, we will explore sinusoidal functions and understand how RF signals are fundamentally built from sine waves. If you found this useful, like the video, subscribe, and follow for the next lesson.